Good day everyone, my name is Fitri and today I will be presenting my topic for PHY568 Electricity and Magnetism, focusing on electromagnetic field theory. Next, for introduction, electromagnetic field theory explains how electric charges produce electric and magnetic field that interact with other charges without direct physical contact. These interactions are described mathematically using vector calculus, which allow field quantities to be expressed in terms of magnitude, direction, and spatial variation. The theory forms the foundation for analyzing electricity field behavior, charge distribution, and electromagnetic wave propagation in space. Next, vector analysis. Electromagnetic field theory relies heavily on vector analysis because most field quantities have both magnitude and direction. Scalar quantities such as electric potential have magnitude only, while vector quantities like electric field intensity require both magnitude and direction. A general vector in Cartesian coordinates can be written as A equals AX plus AY plus AZ. This representation allows us to analyze field component along each coordinate axis separately. Next slide is about dot product and cross product. The dot product between two vectors is defined as A dot B equals AB cos theta. This operation produces a scalar and represents the projection of one vector onto another. It is commonly used in electric flux calculations. The cross product is defined in magnitude as magnitude of A cross B equals AB sin theta. In component form, it can be written using the determinant of unit vectors and components. The cross product produces a vector perpendicular to both original vectors and follows the right-hand rule. Next slide is about coordinate systems. Different coordinate systems are used depending on the symmetry of the problem. In Cartesian coordinates, we use x, y, and z axes. In cylindrical coordinates, the variables are rho, phi, and z. In spherical coordinates, the variables are r, theta, and phi. Choosing the appropriate coordinate system simplifies mathematical evaluations of electromagnetic fields. Next slide, del operator. The del operator represented by the symbol nabla is a vector differential operator used to describe spatial variation of field. In Cartesian form, it is written as del equals AX partial over partial X plus AY partial over partial Y plus AZ partial over partial Z. It performs three main operations. The gradient written as del V gives the rate of change of a scalar field. The divergence del dot A measures outward flux density. The curl del cross A represents rotational behavior of a vector field. These operations are fundamental in electromagnetic field equation. Next, electric charge. Electric charge is a fundamental property of matter responsible for electromagnetic interaction. Charge may exist as point charge, line charge density, surface charge density or volume charge density. The total charge in a volume can be expressed as Q equal the volume integral of rho and dV. Charge conservation states that charge cannot be created or destroyed, only transferred. Next, electric field. The electric field is defined as force per unit positive test charge. E equals F divided by Q. For a point charge Q, the electric field at distance R is given by E equals 1 over 4 pi epsilon naught times Q over R squared in the radial direction. The direction of the electric field is outward for positive charge and inward for negative charge. A static electric field exists when charges are stationary and field quantities do not depend on time. Under electrostatic conditions, partial over partial T equals 0. The electric field is conservative, which means del cross E equals 0. Because of this, the electric field can be expressed as the negative gradient of electric potential. E equals negative del V. This establishes the relationship between electric field and potential. Next slide, electric flux and Gauss law. Electric flux is defined as the surface integral of the electric field. Phi E equals the integral of E dot ds. For a uniform field over a flat surface, Phi E equals E a cosine theta. For Gauss's law in integral form states the closed surface integral of E dot ds equals Q enclosed divided by epsilon naught. For indifferential form, del dot E equals rho V over epsilon naught. This equation relates electric field divergence directly to charge density. Next, time varying field. When field quantities depend on time, the system becomes dynamic. The electric field becomes a function of space and time. E equals E of x, y, z, t. Under dynamic condition, partial over partial t is not equal to 0. Faraday's law in integral form states the closed line integral of E dot dl equals negative rate of change of magnetic flux. In differential form, del cross E equals negative partial B over partial T. This shows that a changing magnetic field produces an electric field. Next, Maxwell's equation. Maxwell's equations combine all fundamental electromagnetic laws. First, Gauss law, del dot E equals rho V over epsilon naught. Second, Gauss's law for magnetism, del dot B equals 0. Third, Faraday's law, del cross E equals negative partial B over partial T. Fourth, Ampere-Maxwell law. Del cross B equals mu naught J plus mu naught epsilon naught partial E over partial T. These four equations provide a complete description of electromagnetic behavior. In conclusion, electromagnetic field theory provides a structured mathematical framework for describing how electric charges generate electric fields and how these fields interact in both static and dynamic conditions. By applying vector calculus and Maxwell equations, electromagnetic phenomena can be analyzed systematically in space and time. That concludes my presentation. Thank you for attention.